Okay, so in this video we're going to calculate the light intensity at a certain point with regards to two different situations. One is in the perception of a photographer and the light intensity upon the subject that he's trying to photograph, and the second one is the irradiance incidence, that's the rays coming off the sun and how much in watts per metre squared it is inflicting upon each of the planets. Now we're going to use some formulas to calculate the ones at each planet, and also here I'm going to show you how to calculate it with regards to photography. So we're going to start with this one first. If we can understand this one, then we can move on to this one and we can mess around with some formulas. So light intensity is given by this formula. It's 1 over the distance squared. Now in this one here, the distance can be in any unit of measurement you like, feet, meters, miles, whatever you like, that's fine. So in here, I'm going to use this here all as in meters. So this light here is shining on these 3 points here. We're going to calculate the intensity at each point. So using this formula, our distance here is going to be, distance here is 1. So this one here is 1 meter away. So intensity at D equals 1. Our intensity equals 1 over 1 squared, which just equals 1. So I'm just going to write that in decimal form. This one here at D equals 2. So now we're twice as far away, but the light intensity is not going to be reduced by a half, it's going to be reduced by a little bit more. So here the intensity equals 1 over the distance, which is 2 squared, which equals a quarter or 0.25. So basically it's a quarter of the intensity from here to here. Now what if we get to this point with regards to this point here? So here our distance is 3 and our intensity will be 1 over 3 squared, which equals 1 over 9, which equals 0.1111 recurring. Okay, so that's the differences in the light intensity at each of these points. Now to move on to this one, we're looking at the power given off the sun towards each of the planets. Now what we do know is the average annual irradiance incident on the Earth coming from the sun is 1361 watts per metre squared. So how are we going to calculate the average annual irradiance incident at Venus and Mercury, knowing that we know that this one at Earth is this amount? Well, we can manipulate this formula a little bit and we can say that, let's do it on here, I equals 1 over D squared. Now we know that for the Earth, so we call it Earth as number 1 and the distance number 1. Now if we want to measure it as a ratio between Venus and Mercury, we know a ratio is just going to be I1 over I2, for example. Now I1 we know is 1 over D1 squared. Now what about the I2? So the I2 we know, we just ignore the I1, we go 1 over I2 is now the reciprocal of this one. So now that will be D2 squared over 1. So now I1 over 2, we can now just put these two together and that will be D2 squared over D1 squared. Then that will give us our ratio between the two. Now if we know I1 over I2 is that, then what we can say is by cross multiplying, we can say that I1 times D1 squared is equal to I2 times D2 squared. And if we want to isolate each one of these, then all we have to do is just usual rules of algebra. Now we know the distances, which I've got over here written down. These are just the average distances. These will change depending on where it is on its circulation around the sun. So if we want to isolate, for example, the I2, we can just divide both sides by d2 squared. So we can get I1 times d1 squared divided by d2 squared equals I2. And we can also take this I1 out of here and just call that d1 squared over d2 squared times I1 equals I2. So now this formula here, we can make good use of that because we've got all the distances and we've only got one of the irradiance incident, which is at the Earth. So now if we can put these values here into this formula, then we can work out the power of the sun on each one of these. So let's go and work out the one at Mercury first. So I'm just going to rub these out now, just keeping this formula. So distance 1 squared. So distance 1 is going to be the Earth, which is 150 times 10 to the power of 6. So 150 times 10 to the power of 6, and that's going to be squared. So that's going to make quite a big number. So I'm going to divide this now by the distance 2. So we're looking for Mercury. So that is 58 times 10 to the 6 squared, and times I1. So the irradiance incident at the Earth is 1361. So times 1361. Okay, looks a little bit messy, but what we can do is here we've got two common numbers here. We've got 10 to the power of 6, which is our million constant. So we can now take those out, and now we've got 150 squared divided by 58 squared times 1361 equals our irradiance incident at Mercury. So equals I2. So 150 squared divided by 58 squared times 1361. I'll just get my calculator for that. So 150 squared divided by 58 squared. So that is approximately 6.69. So we've got 6.69 times 1361. So times that together, that's going to give us very close to 9,103. So that's watts per meter squared, and that's at the planet Mercury. Okay, so now we can work it out now for Venus. So now we could just go straight into this formula here. We can take this one off the board now because we know it. So now we need, so at the Earth it's 150 times 10 to the 6 squared over 108 times 10 to the 6 squared times 1361. So as we did before, we can cancel these 10 to the 6's out. So now we've got 150 squared divided by 108 squared, which is approximately 1.93. So 1.93 times 1361. So that's going to give us approximately 2,625.4. And that's watts per meter squared. So if you go on, we could calculate all these for all the other planets, for example Saturn or Pluto or Neptune or whatever, using this formula that we've used here and manipulated a little bit, and it would all come from the same way that a photographer would use to calculate the light intensity when he's trying to photograph his subject. Okay, thank you.